there's a symbol that you're going to see that you may have not seen before a lot in this chapter, and it's an R with an extra line in the front. It's all real numbers, but they're gonna throw a little superscript on it. So you might also see R2. This means we are working with two number lines that can use all real numbers. So like an x-axis and a y-axis. So it's working with ordered pairs. So it's like the two-dimensional plane. So that superscript that you see on the R tells us how many axes we're dealing with, how many variables we're dealing with, what dimension, right? So this book likes to use this symbol a lot. Our last book didn't use this terminology at all, but this book likes to use it. So this number includes the independent variables and the dependent variables. So in R2, there's always going to be one dependent variable. Otherwise, it's not going to be a function. And then all the rest of them are independent variables. So there's one independent variable and one dependent variable. In R3, which contains x, y, and z, there's only one dependent variable ever, and that's the z, which leaves the other two, x and y, as independent variables. So we could have R6 be A, B, C, D, E, F. I am getting a little excited. But let's see if we can see a pattern in the two above.
It's always, okay, A, B, C, D, E, dependent, F, dependent.
Yes. There are 5 independent variables, A, B, C, D, and E. There is one dependent variable, and that is F, the last one. So quick review of planes. That's the first equation that we see. That's an actual equation that involves all 3 of our variables in 3 dimensions. There are 2 pieces of information that we need to write the equation for a plane. Does anybody remember what they are? A plane in 3-dimensional space could be at a particular angle, and it could go through particular points that would make it have a different equation than other planes that are at different angles and go through different points. But any plane in space actually would go on forever in every direction. We need to know at least one point that's on the plane and a vector that's normal to the plane. So if we have point P, x1, y1, z1, and normal vector n, which has components a, b, c, there are 2 formats for the equation for the plane. They were very closely related. One of them is really just the basic setup, and then the second one is where we just multiply it out. So the definition for a plane are all the points where the normal vector is at a 90-degree angle to some other vector that connects with P. Q is some x, y, z in the plane. Q is some x, y, z in the plane that we don't know. P is some x1, y1, z1 in the plane that we do know. So Q represents any point in the plane. We do know one point in the plane P. Vector PQ, we can get component form for that by doing the Q's minus the P's. And then if n is a normal vector to the plane, PQ is in the plane, and n is normal to the plane, what's the dot product of 2 normal vectors always going to be? It's always going to be 0. So this is where the formula for, or the equation for a plane comes from. The equation for the plane is any point x, y, z in the plane that when you create a vector with P, its dot product with n is 0. So now if we create vector PQ, to create vector PQ, we do the Q's minus the P's. Now Q is just a variable vector. It represents any possible point that could be in the plane. So Q has the variables x, y, z in it. P has point values though. It's got coordinate values, x1, y1, z1. So what would the component form for PQ be? How do we find component form if we know the beginning point and the ending point? We do ending minus beginning. So I'm going to do x minus x sub 1, y minus y sub 1, z minus z sub 1. That's vector PQ. And then I'm going to dot that with n, and it will equal 0, because PQ is in the plane. N is normal to the plane. That is always going to be true, and the dot product of two vectors that are normal, the dot product of two vectors that are 90 degrees is always going to be 0. So PQ dotted with n, dot product is where we multiply corresponding components and add the results. So PQ dotted with n, well, n has components a, b, and c. So this is going to be a times x minus x sub 1 plus b times y minus y sub 1 plus c times z minus z sub 1. And according to properties of dot product, that should equal 0. This is standard form. And if we were to go ahead and work out our algebra on that, it would be general. If you're ever asked to compare planes, like see if two planes are parallel, see if two planes are perpendicular, see what the angle between two planes are. So if you're ever asked to compare two planes, all you have to do is compare their normal vectors. Just see if the normal vectors are parallel, if the normal vectors are perpendicular, what the angle between the normal vectors are. Because whatever's going on between those planes, the exact same thing is happening between the normal vectors. And that's because of properties of geometry. Even if you're just given the general form for the planes, remember you can get the normal vectors from the coefficients. If I wanted to know what was going on between those two planes, so maybe like the angle between them or something, the normal vectors for those planes would have the exact same angle between them. Do you remember back to geometry when you learn transversals and vertical angles and opposite interior angles and all that stuff? This angle here is a corresponding angle to this angle here. They will always be exactly the same. So if you ever have to compare two planes and what's going on between two planes, whether they're parallel or perpendicular or just calculating the angle between them, you can always just pull their normal vectors out and figure out what's going on between their normal vectors. Because we've talked about previously how to figure out if two vectors are parallel or perpendicular, or calculating the angle between two vectors.